So welcome to Math 150, multivariable calculus. This is lecture 27. So what I want to do today is I want to prove the fundamental theorem of calculus. So you do not get the name fundamental lightly. Can anybody name any other fundamental theorems that you've seen so far in your career? Any other fundamental theorems you've heard of? So there's two you should have heard of by now. One is the fundamental theorem of algebra. If I give you a polynomial of degree n with complex coefficients, then it has n complex roots. And this is amazing. If I give you a polynomial with integer coefficients, the roots are not integers in general. If I give you a polynomial with rationals, the roots are not rationals. With reals, the roots are not necessarily reals. Once I introduce the square root of -1, I don't need to do anything else. Any polynomial of degree n with complex coefficients has n complex roots. The other one you might have heard of is the fundamental theorem of arithmetic. Every integer can be written uniquely as a product of primes in increasing order. This is why 1 is not considered a prime. A lot of people say a number is prime if its only factors are 1 in itself. Well, by that definition, would 1 be a prime? So the definition is a prime is a number that has only two positive factors, 1 in itself. 1 is a unit. And the reason we make 1 a unit is for the fundamental theorem of arithmetic. It's very useful to be able to write every number uniquely as a product of primes. So today we're going to prove the fundamental theorem of calculus in one variable. It's going to be a great way to review a lot of the stuff we've seen. It will help us transition to several variables when we're trying to find areas under curves. I will not prove the analogs of integration and fundamental theorems in several variables. Instead, I'm going to just concentrate on the simpler one-dimensional case, as this highlights what's going on. I am not going to prove the fundamental theorem of calculus in the greatest possible generality. I will assume our functions are nice. You can play games, and if you're a mathematician professionally, this is what you often do. What is the weakest assumption I need in order to be able to prove this result? Now, we're going to assume our functions are continuous. We're going to assume they're differentiable. We're going to assume the derivatives are continuous. We're going to assume intervals are finite. We're going to make things easy for ourselves. If you want to, you can drop a lot of these assumptions, but not all. When we get to functions of several variables, there will be some surprises, and I want to make sure we leave time to emphasize that. But what we'll do will be more than enough. In one variable, we can often get nice closed form expressions for the antiderivatives, which will make things very simple. And the fundamental theorem of calculus is going to tell us that the area under the curve of y equals f of x is the antiderivative of f at b minus the antiderivative of f at a. Well, actually, not quite. I used one word incorrectly. Did anybody hear which word I used incorrectly? It's the antiderivative at b minus the antiderivative at a. How many derivatives does a function have? So how many derivatives? So I give you a function, how many derivatives does it have? How many first derivatives does it have? 1. How many antiderivatives does it have? How many functions have this as its derivative? Infinitely many. They all differ by a plus c. And if you remember your physics, what matters when you're doing, potential and kinetic, the change in potential is the change in kinetic. The potential energy doesn't matter. What matters is the change in potential. And you can shift your potential value by adding a constant. So it's not the antiderivative at b, it's an antiderivative. Okay, so we're going to need a couple of key lemmas. So the first is the intermediate value theorem. And so my daughter is preparing some notes for us. She uses a little bit stronger language than I will write down. These are essentially the no-shit theorems. These are extremely intuitively obvious. We have to prove them. Essentially, the intermediate value theorem is there is no such thing as a transporter. You cannot move instantaneously from one point to another. So if f is continuous on AB, then if capital C is between f of A and f of B, there is a little c in the interval AB with f of little c equals big C. So another way of saying that, ooh, that's terrible. So another way of saying that is if my function is, here's A, here's B, you give me any value between A and B, then there is no way for me to continuously go from A to B to f of B without crossing this line. Okay. I can't connect from down here at f of A to up here at f of B without going through C. I might go through it many times. There could be many different places where that holds. There's a lot of ways to try to prove this. I'm not going to prove this in detail. I'm just going to give you a rough sketch. It's similar to what we saw with the divide and conquer earlier. Look at the midpoint. At the midpoint, am I equal to f of A? Am I equal to f of B? Am I equal to f of C? What is my value? Well, let's just look at the midpoint and see, am I more than big C or am I less than big C? If I'm more than big C, I'll look between A and the midpoint. If I'm less, I'll look between the midpoint and B. And each time I'm going to get a smaller and smaller interval. So I'm going to have a string of left endpoints where I'm less than C, and I'll have a string of right endpoints where I'm greater than C. And the distance between them is going to be getting smaller and smaller and smaller and smaller. But my function is continuous. And the size of those intervals is going to 0. So if they're going to 0, and the left is always less than C, or less than equal to C, and the right is always greater than equal to C, they've got to converge to a common value. What's the only possible common value? So what's the only possible common value? C. So the proof, look at a sequence of midpoints. So left is less than equal to C, right is greater than equal to C. Keep subdividing, converge to a common value. Okay, we can write this up very rigorously with math notation, but intuitively, this is what's going on. You just keep getting smaller and smaller and smaller. Each time you iterate, the distance is half of what it was before. And since the function is continuous, this is going to force it to become big C. If the function was not continuous, then this, all bets are off. I could define the function to be -1 up to here, and then 1 from there onward. And then I wouldn't have to have such a value. Okay, any questions on the intermediate value? All right, anybody know which theorem is next? The mean value theorem. So the mean value theorem, MVT. So if f is continuous and differentiable on AB, there is a C in AB such that f prime of C is f of B minus f of A over B minus A, or f of B minus f of A is f prime of C times B minus A, i.e., at some time, the instantaneous speed equals the average speed. This is another no shit theorem. Okay, imagine you're always traveling. Well, here, somebody give me an average speed on the highway. 70. Obviously, this is nothing your professor would do on an eastern state, but let's say the average speed is 70. So case 1, always travel less than equal to, less than 70. Can the average speed be 70 if we're always traveling less than 70? No. All right, everybody agrees? What's the next case? So case 1, we're always traveling less than 70. What should case 2 be? Always 70. So we always travel greater than 70, also contradiction. So we're in case 3. Either always 70 or at some point, well, I guess it's not always that, either at some time we're 70, in which case we're done, or at some point we're less than 70 and another point we're greater than 70. Well, if at some time we're 70, have we found a time where the average speed is the instantaneous speed? Yes. So really the only thing we have to worry about is we can't be traveling 70 ever. We're not always less than 70, we're not always greater than 70. So at some point in time, we're less than 70, at another point in time, we're greater than 70. How do we now finish the proof? What do we use? Intermediate value theorem. There's probably a reason we did the intermediate value theorem first, right? So, oops. So by intermediate value theorem, we hit 70 at some time. Okay. Who here has ever watched the TV show Friends? Except for, I think, 2 episodes, how does the title of every episode begin? The one with. So for the rest of today, if we ever need to bound something, this is the one, this lecture is the one with the mean value theorem. The mean value theorem is our go-to result. It is a poor mathematician's Taylor series. You can look at it as, you know, f of b minus f of a is f prime of cb minus a. Well, we could actually rewrite that if we wanted to as f of b is f of a plus f prime of c b minus a. It's telling us if we move just a little bit, how much have we changed? It's equal to f prime of c times the amount we've moved. The problem is we don't necessarily know what that c is. This is an existence statement. There is some c. Well, what is that c? I don't know, but there is a c that works. The last concept we need is that of boundedness. So we say f is bounded by b if f of x is always less than or equal to b. Exactly what you would expect. For a lot of things, we just need to know that something is bounded. I don't necessarily need to know the best value of the bound. I just need to know that it's bounded so that the process can begin. So for example, somebody give me a function. Quickly, some function. X squared plus 3, something else. Give me another. No, just give it one variable. Plus 3x, something else. You said 2x cubed? Let's say I give you this as my function. Okay. I want to show, and let's say we want x in the interval -1, 10. Okay. The absolute value of f of x is going to be less than or equal to the absolute value of x squared plus 3 times the absolute value of x plus e to the absolute value of x cosine 2x cubed plus 1701. Is everybody comfortable with that? That if you have the absolute value of a quantity, it's less than or equal to the triangle inequality than the absolute value of the pieces, because I lose the possibility of cancellation. I have x going between -1 and 10. How large could x squared be? So what's the largest x squared could be on this interval? 100. This is going to be less than or equal to 100 plus 3. How large could 3 times x be? 30. But if you said 300, that's also correct. 3 times x is also at most 300. You can do better. You can do it's at most 30, but it's 300 would be fine. What about e to the absolute value of x cosine 2x cubed? X goes from -1 to 10. What's the largest that could be? Or give me something that you know is larger than that. Okay, but infinity is too much larger. It works, but I want a finite number. How large could this exponent be? What, you don't have to give me the best result. I'm sorry? 10. Why 10? Yeah, cosine is between -1 and 1. It's going to be at most 1. So this is going to be at most e to the 10. It is extremely unlikely that it is as large as e to the 10, because that would mean I need 2x cubed to have a cosine of either 1. No, not happening. But I don't care. I just want to show that this is bounded. As a nice calculus exercise, you could try to figure out what is the largest value of e to the x cosine 2x cubed, or what is the largest value of this whole function. I don't care. Does everyone agree that this is less than or equal to 10 to the 1,000? I really don't want to add these numbers. And if I write 10 to the 1,000, that's going to be more than enough to be safe. What we're doing is we're showing at the end of the day that the area under the curve converges to the difference of the antiderivatives. I'm only going to be using the boundedness to show that certain things converge. It's going to vanish in the limit. It doesn't really matter. Now, how many of you remember proving the fundamental theorem of calculus in high school in Math 140? How many of you don't remember, but you at least did it? Okay, this is something that you really need to have, in your bailiwick. If you are, a mathematician, you need to have seen at least once in your life a proof of the fundamental theorem of calculus. We have a bunch of things that only matter to help us get to where we want. Now, if we're doing finite Riemann sums, which we'll do again in a moment, then the lower number we use for the bound, the faster convergence we'll get. And so if we care about a finite approximation, then being cavalier like this could be quite bad. But if we only care about what's going on in the limit, it doesn't matter. This is just a helping quantity. Does anybody remember anything else from this class where we introduce something that we only care about because it helps us get to what we really care about? We don't really care about its value. It's just to help us to get to something else.
I don't remember what the name is, but is it sigma?
Not sigma, but it's close.
Okay.
Lagrange multipliers, right? The lambda from Lagrange multipliers. We don't care about lambda at the end of the day. We care about lambda because it helps us find the point. It's the same thing here with this bound. It's just going to help us prove what we want. All right. Are we ready to prove the fundamental theorem of calculus? One day, one lecture. So, fundamental theorem of calculus. So there was a comment about the Mets shirt that I'm wearing today. This is in honor of a Williams alum who is working for the Mets, who's coming in. If anybody is interested, he will be speaking in this room at 10 o'clock. If you really want to upset me, there are two things you can do. Anybody know what one of them is? You use wrong notation. And the other one is I don't mind about insulting the Red Sox. It's Yankees over Red Sox. If you do that, bad notation or incorrect notation or incomplete, this will really upset me. And the reason it will upset me is because it increases the probability of making an error. Notation is extremely important. You want to be able to look at things and see what's going on. As you go further and further and further, in your careers, you're going to have incredibly complicated formulas, and you want to be able to quickly glance down and see what's going on. You don't want to make things so concise that they're useless. I think we did Feynman's all of physics in one equation, the unworldliness equals 0, where he takes every physical law and subtracts the right-hand side from the left-hand side and squares it and then adds it up, so that the only way that this can be 0 is if every law of physics is satisfied. And Feynman remarks, we've now reduced all of physics to one equation and we've made absolutely no progress. This is just extremely compact, unuseful notation. Be very careful, really think about what notation you use and why. So the fundamental theorem of calculus, let f be a continuous and differentiable function on a finite interval AB with f prime of x less than equal to big B for some b. So f is bounded. Let big F prime equal little f. So big F is any antiderivative. Then the area under the curve y equals f of x from x equals a to x equals b is f of big B minus f of a, and denote this by writing integral from a to b of f of x dx. So if you really want to upset me, drop the word area. If you just say the integral from a to b of f of x dx equals big F of b minus big F of a, that has no content. That's just a definition then. The content is that this represents area. So what we're really saying is the area is the integral from a to b of f of x dx is big F of b minus big F of a. And if you don't say area, you're wrong. Okay, well, when we look at this, we can see now why it doesn't really matter which antiderivative we choose. Because imagine you have two runners who have identical speeds and direction at every moment in time. What's the distance between them? Is it increasing, decreasing, or staying the same? If you have two people who at every moment in time are running at the same speed in the same direction. Yeah, the distance between them is not changing at all. Does that mean they're in the same place? No, it just means they differ by a constant in terms of their location. So if you think of little f as speed and big F as location, if I say I've got two functions that have the same speed, then their locations have to always differ by a constant. And that's why when we look at this over here, it's not going to matter, because if I add 5 to F, I would add 5 to F of B, I would subtract 5 to F of A. All right. So now we're going to go into Riemann sums. And so what we're going to do is, without loss of generality, I'm going to assume my interval is 0, 1, just to make things nice. And so I have my function, and what I'm going to do is I'm going to chop it up into pieces. So this is going to be x0, x1, x2, dot, dot, dot. Xk will be k over n, and so on and so on and so on. And the idea is for each one of these, you can do the left Riemann sum. We use the left endpoint to make your rectangle. You can do the right Riemann sum. We use the right endpoint. You could make a trapezoid. There's so many different things you can do. We're going to try to find a bunch of rectangles and estimate the area under the curve by summing the area of the rectangles. And the hope is that the more pieces we take, the more accurate we're going to get. Okay? Now, the problem is there could be a lot of variation from the left value and the right value. And so we want some better way of looking at things. And so what we'll do is we'll blow things up a little bit. And so here's xk, which is k over n, and here's xk plus 1, which is k plus 1 over n. And let's say, here's my function. Okay. And so what I can do is I can find an upper and a lower bound. So I'm going to look to see where is my function smallest, and I'll call that point L sub k for the lower sum. And I can look to see where's my function largest. Just change it a little bit, so I'll have it shoot up just a little bit before. And so over here will be U sub k for my upper sum. Thank you. And so I'll draw it on the other direction like this. And so the idea is on the interval xk to xk plus 1, we have f of lk is less than or equal to f of x is less than or equal to f of uk. So implicit in what I'm doing here is that my function does have a place where it's largest and it does have a place where it's smallest. So I always want to be clear when I'm assuming something. I am assuming that on every interval like this, the function has a place where it's largest and smallest. You can prove this using some continuity results. And what you can do is you can keep getting string of places where the function is getting smaller. By continuity, it's going to converge to something. It's not, you're not going to have something going off to minus infinity because the function is bounded. Okay, so there are such points, but you do have to be a little bit careful and prove that. Or you just stay with nice functions where this is true. So if I want to estimate the area from xk to xk plus 1, I would get that flk times 1 over n is going to be less than, I'll use red, I guess, is going to be less than or equal to the integral from xk to xk plus 1 of f of x dx, and that'll be less than or equal to f of uk times 1 over n. Is everybody comfortable with that? That on each interval, I can look at what is the area, and this is the area under f in this interval. Everybody's comfortable? Lower bound, upper bound. And now what I'm going to do is I'm going to just sum over all the pieces. So sum over all the pieces. And then what we'll get is we'll get L sub n, which is the lowest sum with n pieces. This is going to be the sum. K goes from 0 to n minus 1 of f of lk 1 over n. This will be less than or equal to the area, and that'll be less than or equal to the sum k goes from 0 to n minus 1 of f of uk times 1 over n, and we'll call that un for the upper sum. Okay. What do you hope happens as n gets larger and larger and larger? What would you hope happens? Want to try? What do you think? What do you hope would happen as n gets larger and larger and larger? Okay, and what would you want them to converge to? Hopefully the area. Do you think the lower sums are always going to be strictly increasing to the area and the upper sums always strictly decreasing? It would be nice if that's true, but unfortunately no, because when I go from 5 partition points to 6, that could change where the upper and the lower values occur. You can make things nicer if you do what's called a dyadic decomposition. So you go from 2 points to 4 points to 8 points to 16 points and so on, that every time for the next level, you just divide each piece in half. And if you divide each piece in half, then you will get the lower sums are going up and the upper sums are going down. So what we want to show ln and un converge to a common value. If yes, has to be the area. There's nothing else it can be because the lowest sum is always less than or equal to the area. The upper sum is always greater than or equal to the area. So if they converge to a common value, the only thing that can be is the area. So we have to study the upper sum minus the lower sum, which will be the sum k goes from 0 to n minus 1. And I'll have an f of lk over here, and I'll have an f of uk over here. So I want to show that this difference goes to 0. Well, let's think about it. As n gets really, really large, what happens to 1 over n? It goes to 0. That's great. Unfortunately, how many summons do we have? How many summons do we have? How many terms do we have? Not n minus 1. We start at 0. We have n terms. So even though we have a 1 over n, which is really small, because we have n terms, a really small number taken a humongous number of times is going to be potentially large. So unfortunately, the fact that 1 over n is going to 0 is balancing the fact that we have more and more summons. Okay, so however, we still have this difference between the largest and the smallest values in the intervals. As long as we can show that that goes to 0, then we're in great shape. So we need to show this goes to 0. Show this goes to 0. Okay, so if we're going to do that, so let's study, I'm going to stop using colors now, f of uk minus f of lk. Can anybody think of a theorem we can use to study this? What could we use to study this? What theorem? Yeah, the mean value theorem, right? Earlier today, when in doubt, use the mean value theorem. This is the one with the mean value theorem. Anytime you are stuck, use the mean value theorem. So this equals f prime at some point, let's call it ck, times uk minus lk by mean value theorem. So if we take the absolute value, we get f of uk minus f of lk is less than equal to, is equal to the absolute value of f prime of ck times uk minus lk. And again, we have our function, looks something like this. Here's xk, here's xk plus 1, here's uk, here's lk. By assumption, what do we know about f prime of ck? How large can that be by assumption? I'm sorry? In between what? What are we assuming about the first derivative? We're assuming the first derivative is so we're assuming that f prime of x is always less than or equal to some big B. We don't care what it is. We're just assuming that there is some big B that works. So this is at most big B by assumption. What about UK minus LK? What's the greatest distance UK and LK can be from each other? sorry? Yes, but B minus A is too large. Remember, UK and LK live in the same interval. They live somewhere between XK and XK plus 1, between K over N and K plus 1 over N. How far are XK and XK plus 1? 1 over N. So what's the maximum distance UK and LK can be from each other? 1 over N. So this is at most 1 over N, as each is in the interval from xk equals k over n to xk plus 1 equals k plus 1 over n. Substituting, and we get un minus ln is less than equal to the sum, k goes from 0 to n minus 1, big B times 1 over n times 1 over n. And the reason is, we have FUK minus FLK. We said that this part is at most B times 1 over n, and we still had a 1 over n. I'm not putting an absolute value on the upper sum minus the lower sum. Well, I don't have to. The upper sum is going to be at least as large as the lower sum. So I don't have to worry about, should there be an absolute value sign on the left? So this is going to be equal to B over n squared times the sum, k goes from 0 to n minus 1 of 1. This is almost the easiest sum I can give you. I'm adding 1 a total of n times. What's 1 plus 1 plus 1 n times? Not infinity. We're adding it n times, not infinitely many times. So you want to 1 times n. So this is just going to be b over n squared times n, or it's b over n. And as n goes to infinity, what does this do? It goes to 0. And that finishes the proof. So we'll put a little QED box. This finishes the proof that the upper sum minus the lower sum goes to 0. Okay. We're in great shape. We've got over 10 minutes left. We know the upper sum and the lower sum converge to a common value. We know that common value is the area under the curve. The only real assumption we've made so far is that on any interval, a continuous function takes on its largest and smallest values. And again, we could prove this rigorously if we needed to. I'm hoping that this seems clear enough that you're willing to accept it, but I always want to be very explicit about what are we assuming. So now we need to show that the area under the curve is equal to the antiderivative at B minus the antiderivative at A. Any thoughts on what theorem we should use to show that? Well, that's what we're trying to prove. We're trying to prove the fundamental theorem of calculus. What theorem do you think we should use now to try to show that the area under the curve, that the upper sum and the lower sum converge to the antiderivative at B minus the antiderivative at A? What theorem do you think we should use? Yeah, the mean value theorem, right? When in doubt, use the mean value theorem today. So now on the next part of the proof, let's consider the following. 14 minus 1 plus 17 minus 14 plus 110 minus 17 plus 1701 minus 110 plus 24601 minus 1701. What does this equal? I'm taking too long. Taking way too long. Nope, close though. 24600. One less than Jean Valjean. So this is a telescoping sum. I don't need to keep adding line by line by line. The 14 and the negative 14 cancel. The 17 and the negative 17 cancel. So it just reduces to 24601 minus 1. So it's just 24600. Sum. So telescoping sums are great. You only need to study the first term minus the last term. So let's consider the sum k goes from 1 to n of f of xk minus f xk minus 1. Okay, so what would this be? This would be fx1 minus fx0 plus fx2 minus fx1 plus fx3 minus fx2 dot 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 plus fxn minus fxn minus 1. What would this sum equal? Excellent, f of xn minus f of x0. It's a telescoping sum. So we now know that the sum k goes from 0 to n, I'm sorry, k goes from 1 to n of f xk minus f xk minus 1 is equal to f of xn minus f of x0. But f of xk minus f of xk minus 1, I guess I shifted my interval over by 1. This is just going to be f prime at some point. I need a letter. I'll use m for the mean value theorem. I'll call it m sub k times xk minus xk minus 1. Why is this true? So why is this true? So I'm claiming big F of xk minus big F of xk minus 1 is big F prime at some point in the interval times xk minus 1. Okay. And so it's the mean value theorem. It's the mean value theorem again. This is just the mean value theorem. But it's the mean value theorem applied to big F. So f of xk minus f of xk minus 1 is little f at mk times 1 over n. So if you think about what's going on, this, so on the interval xk minus 1 to xk, we have f of lk minus 1 less than equal to f of mk less than equal to f of uk minus 1. Because on this interval, f of mk can't be smaller than the smallest value in the interval, and it can't be larger than the largest value in the interval. So we get, okay. So we get that the lowest sum is less than equal to the sum of fmk times 1 over n is less than equal to the upper sum. K goes from 1 to n. Because on each interval, this value is at least as large as the smallest, and it's not larger than the largest. So if I multiply by 1 over n, the area here has to be at least as much as the lower bound for the area, and it can't be more than the upper bound for the area. So I've sandwiched this quantity. let's record this. But we know, does anybody remember what this sum in the middle is? What did we show the sum equals? Not 0. So let's go back 2 pages. Here we have f of xk minus f of xk minus 1 is just f of xn minus f of x0. And if we looked by the mean value theorem, f of xk minus f of xk minus 1 is just f prime of mk, that's just f of mk times 1 over n. So really, when we look at what do we get if we sum this over all k, that's just summing this over all k. That's just summing f of xk minus f of k minus 1 over all k. But we know that is just f of xn minus f of x naught. So when we come over here, this is just f of xn minus f of x0. And what's wonderful is this answer does not depend on how we partition. It doesn't depend on what we use for the bound. Now we let n go to infinity. As n goes to infinity, what does un converge to? We'll use purple for this because it's so important. As n goes to infinity, what does un converge to? So as n gets larger and larger and larger, what is the upper sum converging to? Not 0. What is the upper sum trying to estimate? The area. It's an upper bound for the area. And what is L of n a lower bound for? The area. So as n gets really, really large, what does the upper sum converge to? It converges to the lower sum. And what's the common value that the upper sum and the lower sum converge to? The area. So you have the area over here. As n goes to infinity, the upper sum converges to the area. And the lower sum converges to the area. Well, actually, it's not zigzagging like that. It's constant, right? The thing I have in the middle isn't changing at all. So what's the only possible value for f of xn minus f of x naught? The area. So thus the area denoted the integral from a to b of f of x dx is big F of 1 minus big F of 0. And this is just using xn is n over n, which is 1. X naught is 0 over n is 0. We're just doing it on the interval 0, 1. If I can do it on the interval 0, 1, I can do it on the interval 3, 17. It just makes the notation a little bit messier. So let's just assume the interval is 0, 1. This is a proof of the fundamental theorem of calculus, and we still have time in the bank. Less than 1 class. And we started a little late. Okay, this is probably the most important result you've seen in your career. This allows us to calculate areas under the curves. We can find the area of a circle now. Now the question, of course, is how do we find the area of the circle? We have to integrate some trig functions. And how do you define the trig functions and whatnot? What do you need? What number do you think you need in defining these trig functions? So when you're thinking trig functions, there's a natural constant that should come to mind, pi. And so the problem is, well, when we define the trig functions and we prove the derivative of sine is cosine, the derivative of cosine is minus sine, does that somehow use the fact that the area of a circle is pi? And if it does, we can't then just use this to then deduce the area of the circle because it becomes literally a circular argument. All right, so this is a good place to stop for today. You should be reading ahead in chapter, whatever the integration chapter is it chapter 15? Okay, my book has a slightly different notation. So again, I've deliberately not given homework problems. I've given you plenty of time. You should be reading far, far ahead in chapter 15 right now. And then we'll slowly over the last 9 classes do the rest of the integration.